Okay, welcome back everyone. This video is going to be on performing operations with numbers in polar form. So we're going to be looking at the addition and subtraction of numbers in polar form, multiplying and dividing numbers in polar form. I'm going to end with a little bit of De Moivre's theorem. So the first question here is, if z1 is equal to 4 cis pi on 6 and z2 is equal to root 2 cis pi on 4, find z1 plus z2. Now, unfortunately, there is no easy way to add two numbers in polar form. In fact, to add or subtract numbers in polar form, we actually have to convert these back to Cartesian form first. Then we can simply add or subtract the real components and add or subtract the imaginary components. So, luckily, we know how to convert between polar form and Cartesian form, so let's just go ahead and do that. Z1 is going to be equal to 4 cos pi on 6 plus 4 sine pi on 6i. Well, cos of pi on 6 is root 3 over 2, so this is simply going to become 4 times root 3 over 2 plus 4 times, well, sine of pi on 6 is a half I. 4 divided by 2 is going to give 2, so this gives 2 root 3 plus 2 lots of I. Okay, if I do z2, well, z2 is going to be equal to root 2 cos of pi on 4 plus root 2 sine of pi on 4. Cos and sine of pi on 4 is both 1 over root 2, which if I rationalize my denominator is root 2 over 2. So therefore I get root 2 times root 2 over 2 plus root 2 times root 2 over 2 I, and I should have added the I up here as well. If I simplify all of that, well, root 2 times root 2 just gives 2. 2 divided by 2 is going to give 1. Same thing, so it's going to be 1 plus I. Now that I have Z1 and Z2 in Cartesian form, well, Z1, let's do this part here in purple, Z1 plus Z2 is simply going to be equal to my real parts added together, which is going to be 2 root 3 plus 1. And my imaginary parts added together, 2i plus 1 lot of I is going to give plus 3 lots of I. Now, if I had a calculator, I could simplify this and get a nice decimal answer. However, if I'm asked for an expression in exact form, well, this is as simplified as it gets. So this would be my final answer. 2 times root 3 plus 1 plus 3 lots of I, where this 2 plus root 3 would be my real component. So sometimes you might see this bit here put in brackets like so, just so we can view this as one big term. This is one real component here of my question. If I was subtracting numbers in polar form, then I just do the exact same thing, but now I'm going to subtract my real parts, and I'm going to subtract my imaginary parts like we did in a previous video. Now, unlike addition and subtraction, where polar form doesn't do a whole lot for us, and we actually need to take our numbers out of polar form, when it comes to multiplying and dividing, polar form makes it much, much easier. When I'm multiplying two numbers in polar form, I have this kind of general rule which I'm going to use to put my numbers in. If I have z1 multiplied by z2, that is simply equal to the modulus of my first complex number multiplied by the modulus of my second complex number. My cis part's going to stay exactly the same, and I'm going to add theta 1 plus theta 2. Just bear in mind, because I'm adding, whether I do theta 2 plus theta 1 or theta 1 plus theta 2, it doesn't make any difference to the outcome or to my answer. So I should write R1 and R2 here as well. So to multiply two numbers in polar form, I multiply the modulus of both my complex numbers, and I add the angle from my two complex numbers. Let's just put this in a little red box so we remember that's the rule. So in this case, if I have Z1 by Z2, that is simply going to equal 3 times 2 cis 3 pi on 4 plus pi on 3. 3 times 2 is going to give 6 cis. Well, 3 pi on 4 plus pi on 3. 12 is the lowest common multiple between 4 and 3. So if I multiply top and bottom, this is going to become 9 pi on 12 plus 4 pi on 12, which is simply going to equal 6 cis 13 pi on 12. Now, one thing we might notice is that this angle here is greater than positive pi, so we do need to convert this into the principal argument form, which is expressing my angle between negative pi and pi. Well, sometimes it can make things a little easier if we just do a quick sketch off to the side to kind of figure out what quadrant does this angle land in. 13 pi on 12 is going to be somewhere around here, where this here is going to be pi on 12, and this here is pi. So 12 pi on 12 is going to be pi, 13 pi on 12 is pi on 12 past 180 or past pi, which is going to put it somewhere around here. If I'm taking my negative angle, I'm going to come back this way. Well, that is simply going to be negative pi plus pi on 12. If I come all the way around here, this can be thought of as negative pi. If I add pi on 12, I'm going to get my new angle, which in this case is going to be negative 11 pi on 12. So I'm going to simplify my angle from 13 pi on 12. So if I scroll down to give myself a little bit of room, I'm going to simplify my angle from 13 pi on 12 to being cis of negative 11 pi on 12. And if we do struggle converting things between negative pi and pi, there are videos on this idea in Unit 2 under our trigonometric identities. Now, if instead of multiplying by two complex numbers, instead I'm dividing by two complex numbers, then I have a slightly different rule, and it's very similar to the rule we use with multiplication. If I have Z1 divided by Z2, that is going to be equal to R1 divided by R2. My cis part is going to stay exactly the same, then it's going to become theta 1 minus theta 2 this time. Now bear in mind, because I have both division and subtraction, my order is important. So whatever complex number goes on top of my fraction, that is the same modulus that needs to go on top of my fraction. It also is going to be the angle that comes first, and then I'm going to subtract by the angle on the bottom of my fraction. Okay, so again, if I pop this here in a little box, I do Z1 divided by Z2 for the same complex numbers. Well, now I'm going to be dividing. That's going to become 3 over 2. My cis part, again, is going to stay exactly the same. And now I'm going to be subtracting my first angle, which is going to be 3 pi on 4, by my second angle, which is going to be pi on 3. Now, again, if I simply just subtract my fractions, that's going to equal 3 over 2 cis. If I raise these both to the lowest common multiple, again, that's going to become 9 pi on 12 minus 4 pi on 12. Now, if I tidy this up, I get 3 over 2 cis and 9 pi on 12 minus 4 pi on 12. Because my denominators are the same, I simply just subtract my top numbers. I'm going to be left with 5 pi on 12. And this time it is in my principal argument form, where it's between negative pi and pi, so I can just leave my angle as is. Okay, the final idea in this video is going to be De Moivre's theorem. Let's just first quickly explore, where does De Moivre's theorem come from? Well, if I have r cis theta, and I raise that to the power of 2. I'm squaring r cis theta, the entire term, r cis theta. I'm squaring all of it. Well, that's simply going to equal r cis theta times r cis theta, just like 2 squared is 2 times 2. Now, I just looked at how we can multiply numbers in polar form. So if I'm multiplying numbers in polar form, well, I know that's equal to r multiplied by r cis, and then it's going to be theta plus theta. Well, r times r gives r squared. So I could simplify this as being r squared cis theta plus theta. Okay, let's just take a quick look at what happens if it's r cis theta to the power of 3, or r cis theta cubed. Well, if I have r cis theta to the power of 3, well, that's going to be equal to r cis theta times r cis theta times r cis theta. Well, if I kind of use my rule from above, I know r cis theta times r cis theta gives r squared cis theta plus theta. If I then multiply by another r cis theta, that's going to give r times r times r cis theta plus theta plus theta. Now I'm going to wind up with r cubed cis theta plus theta plus theta. Okay, I can see I have a pattern forming here, and this is kind of what De Moivre figured out. So, if this is true, well, some of you might immediately identify the pattern. Whatever my indice is here, that's going to be my indice for my R value. Again, 2, 2. If I look at 3, I get 3. Also, whatever number I have up here is the number of times I have theta. If it's to the power of 2, I have theta plus theta. I have 2 lots of theta. If it's r to the power of 3, I have theta plus theta plus theta. I have 3 lots of theta. Now, upon further exploration, if I come to the side so I have a little bit more room, if I look at r cis theta to the power of n, where n stands for any number or any indice, I can wind up with De Moivre's theorem. So if I come across here, r cis theta to the power of n, my rule is going to be equal to r to the power of n, cis, and then I have n lots of theta, or n theta. This is De Moivre's theorem here. I'm going to put this in a nice little red box. So now that I know De Moivre's theorem, I can solve all kinds of polar form questions if they're raised to any indice. 10, 20, 30, I can do all of them. Where this is really, really handy is if I have numbers in Cartesian form and I raise things to powers. Well, if it's the power of 3, for example, I'm going to wind up with 3 sets of brackets all needing to be multiplied. It's going to be really messy and really, really complicated very quickly. So this gives us a really simple and straightforward way of being able to solve any kind of complex number raised to some high indices. If I get a question in Cartesian form and it's raised to an indice, I need to convert to polar form, then I can use De Moivre's theorem. Okay, let's solve this example question. Simplify 3 cis to the pi on 6, all raised to the power of 5. I have De Moivre's theorem, the formula for that just above my question. That means that the simplified version of 3 cis pi on 6 all to the power of 5 is going to be equal to 3 to the power of 5 cis, and it's going to be 5 multiplied by pi on 6. Well, 3 to the power of 5 is going to be simply equal to 243, so that's 243 cis to the 5 pi on 6. So now I have an answer in polar form, all nice and simplified. Okay, so if you need to do 3 to the power of 5 using some long multiplication off to the side, you're welcome to. If this is a tech active exam, then just put 3 to the power of 5 into your calculator and click equals. The key skill here is I can take any number in polar form raised to any indice, and I can get a simplified answer. Okay, that's it for this video. We should be able to add and subtract numbers in polar form, we should be able to multiply and divide numbers in polar form, and we should know how to simplify numbers in polar form raised to large indices.